Please, the next talk that seems to be somewhat kind of within the same topic of image segmentation. Alin, Paraschiv, please, predicting the Geoeffectiveness of coronal mass ejections using machine learning.
Well, hello everyone. Not really the same topic.
Take the microphone.
Hey everyone. Not really the same topic. So I'm the old shameless supervisor who's going to present the work of my then undergraduate student Andrea, who is a computer scientist, and she's done her bachelor dissertation with me. And I am the naive physicist who's trying to understand machine learning slightly better. So we had a very small project on trying to predict the geoeffectiveness of CMEs. And what was the main goal? We tried some classifiers, and we tried to do a binary classifications of whether a CME can be geoeffective or not. And this is complicated. So this talk has no computer vision at all. This is just tabular data. And we tried to play with pure solar data sets instead of going to L1. So this project, instead of doing the most complicated model possible, we did the simplest model. And I hope by the end of it, you'll understand also why. So this uses only solar parameters as input. And we try to associate CMEs with any type of disturbance in the DST index, so including weak storms. And again, this is needed. Okay. So what was the scope? We have a CME. It erupts on LASCO. We see it erupting on LASCO. It gets recorded in the CDAW. And we needed to figure out if such a CME has the potential to induce a geomagnetic event. And we went through simple binary classifiers. So we didn't do a full probability distribution for a CME, because that, again, complicates our situation. So on the data set, there's a good, a bad, and an ugly. The good part is that the CDAW catalog at that time, we could isolate a portion having about 24,000 CME entries. That sounds good. We took mostly all the kinematic parameters from the CDAW catalog. We also took a flare index from NOAA and added it to our parameter setup. So this is not a one-to-one flare to CME association. That doesn't exist. If that existed, we would be happy and this would have worked better. Okay? And we correlated those data sets with the values from the Richardson and Kane catalog. And that comes with its own can of worms. So the Richardson and Kane catalog is pretty much the most widely adopted catalog by the community. That doesn't imply it's the best. And there's a lot of problems. For example, there's a lot of storms in the Richardson and Kane that do not have a unique CME identified with it. From a machine learning perspective, this will induce us with will induce class overlaps. So now the ugly. I mentioned we had 24,000 CMEs in the catalog. About 200 of those are actually geoeffective. So our class imbalance is 99.3 versus 0.7. So at this time, I should just put the microphone down and go home, right? Not really. So yeah, that's a problem. We don't really have enough variables. So in the end, we only had 5 input variables and 1 output variable. And we had a lot of ambiguities regarding the storms themselves, because on top of the Richardson and Kane catalog, not necessarily associating a CDAW CME to a storm, geomagnetic storms can come from all sorts of other places, like co-rotating regions, high-speed streams, and so on. That adds further confusion to this entire setup. So even and everything is dependent on manual labeling done by others. So this is a uniform manifold projection and approximation of the entire input data, and most commonly called UMAP. So this is a new method of visualizing multidimensional data in a 2D representation. And don't ask me about the mathematical details because I tried understanding it and I failed. But the idea was that let's just try our data set, which we formed using the parameters I mentioned previously, and let's see how it looks. So what you see here, the blue represents pretty much the total number of CMEs in this latent space, which does not have an X and Y dimension. The red ones represent the geoeffective CMEs, and you can see a pattern there. So the parameter combinations of geoeffective CMEs seem to link to something that's real. So might as well bring the revolvers out and try to tackle this problem. So because of what I said, we have no idea what machine learning method we could even use to solve this. So we tried all that we could. We tried autoencoders, we tried KNN, we tried support vector machines, we tried neural networks, and actually there's a fifth one. We also did an ensemble model, also logistical regressions, and an ensemble model made by, in the end, after we evaluated all of them, with the support vector machines, logistic regressions, and KNN. So now, we still have the elephant in the room. What do we do with our 0.7% class imbalance? Well, there's a few techniques that we can employ. First thing is that since we did a binary classifier, all our models will say that if a prediction coefficient is 0.5, that's a no. If it's above 0.5, that's a yes. That doesn't work when we want to actually predict geoeffective CMEs. So we manually altered all of the cutoffs for the class to be 0.9 and 0.1. So when the model will say, yeah, this is geoeffective, we mean geoeffective, not probably geoeffective with a 0.5 chance. And the two main tools that we used to actually battle the class imbalance was assigning costume weights and using SMOTE. So with the costume weights, that was pretty simple. A weight is inversely proportional to the amount of data that you have. So pretty much we have weights in, I think in absolute numbers was something about 0.5 for the majority class, for the negative events, and 70 for the minority class. So this is about, so practically we told our models, oh, when you see a geoeffective one, be careful to memorize it. So, SMOTE. This is, I was fascinated by this, as a physicist, by this little gimmick. So this helps you generate artificial data that's compatible with your actual data, with your actual parameter space that you're analyzing. So when using SMOTE, let's say the blacks are the majority class and the oranges are your minority class. And if you pick one of these points at random, right, we can use a KNN-like approach. Let's say K is 2 in this case, and find its two closest neighbors. We pick one of these at random, and then we take a Euclidean distance, in this case, in the actual KNN application on the data sets, we did comparisons of multiple distance metrics. But in this case, this is a simple Euclidean distance, and you add another point in that latent space between the two, again at a random position. Now, you can really, really go wild with SMOTE. So a conservative and good option is to check which points you've added yourself, and then be careful so they're not used ulteriorly in SMOTE. So you don't generate additional data from the additional data. So we only kind of doubled the amount of positive events, and that was enough. So this is a more refined UMAP of the true negatives. And you see it follows this brain shape that's pretty much common with UMAPs for a particular reason that I don't understand. And then, again, our true positives and false positives, again, normally follow these peculiar parameter configurations. Again, it's something that we can't directly physically interpret. But there seems to be 2 or 3 classes of parameter spaces that lead to geoeffectiveness. Okay, and this is the entire UMAP with the entire set of events. So, qualitatively, it might look nice, but quantitatively, this is a flood of metrics that run everywhere. And I'm not gonna torture you with overbearing details, just the main part. So, each of the models actually behave differently. Some of them had reasonable recalls, but very bad precision. Some of them improved the precision at the cost of recall, which is something you would normally expect. All of them had the accuracy and specificity metrics in good to very good terms. So pretty much that means we kind of, our model, and especially the ensemble model from the stack classifier, was very good at saying, oh, don't worry about this CME, this is not geoeffective. Leave it. On the positive side, it finds about 90% of the events in the test case, 80 to 90%, but it gives a big amount of false positives. So pretty much it doubles the amount of false positives. So if you put that in the metric behind, you take again, let's say 24,000 CMEs, you should have 200 that are geoeffective. This will return about 400 of them. So what can we do with this? Actually, we have a simple algorithm which can be run basically near time, as fast as you get solar data. You will have a prediction range in terms of days instead of hours if you're including L1 parameters. And this can be used as a quick look tool to save you time and computational resources if you want to run Enlil or Euphoria or something sophisticated to actually see if that CME is dangerous or not. Might work, might not work. This is kind of, it's a prototype. There's things to improve, and there's a couple of things that we are targeting ourselves. For example, we were wondering whether if we actually introduce an image-based tool, we would instantly improve our accuracy. And that's because all of our false positives, well, about 85% of the false positives were halo CMEs. What we don't have in our data set is whether our halos are front halos or back halos. So that instantly introduces bias in the data. If we can augment a simple computer vision technique to this, which is what we're trying to work on, to just know if that thing is front or back, that would instantly improve our metrics. It would be even better if we would have the CME to flare association. And there's some catalogs, but there's for very short periods compared to the amount of the years that we need to train this on. So we tried the Yashiro catalog, but it's not, the data range is not big enough to crack it. Yeah, and lastly, I'm going to end with the sad news that we don't know how much of LASCO we have left. So even if this works, we don't have any replacement for LASCO to actually get data to run such a model. And I think I'm done. So if you find something useful, please congratulate Andrea. If you want to bash me, I'm here.
Thank you for an interesting presentation. So we have questions, please.
Well, thank you, Alin. I'm hooked by the fact that you talk about the 99.3 versus 0.7% of CMEs that are geoeffective. You mentioned it yourself, What you care about are the halo CMEs. So if you just focus on at least partial halos or full halos, then I believe you will be able to deal with a lot of your class imbalance between positives and negatives. That's one thing. And the second thing is that you might be able to deal with it even more if you have this, like you mentioned, this flare association type of thing. So you can clear relatively easily whether the halo is coming from the backside, the far side, or from the earthward side. So you do not have to deal with all CMEs in there. If you're talking about, a narrow CME of the order, 30 degrees or 80 degrees or 70 degrees of angular opening, then you don't have to worry about this CME being geoeffective in essence. So you can, clean the clutter quite a bit in there than using it. And I wouldn't try the entire data set. I would only focus on those selection criteria because they make your life better.
Yes, Andreas' paper actually has this experiment, so I didn't have time to touch upon that. So we took subsets and we trained them again with 5 times cross-validation with only CMEs that have angular widths of over 60, and then another one with CMEs having angular widths over 120. And but the problem is that the metrics improved, but not really in a too significant way. So it's not enough.
Sure, because
so
you have another
you just
problem.
get a few % more.
Because you have another problem in this case. You need to be able to tell what is the orientation of the magnetic field of the CME, and by just having, just predicting a CME coming your way or not is not going to give you information about the orientation, so you clearly miss a good part of the problem as well. Half of the problem, statistically speaking, right? But it's not really half, because it doesn't go that way or this way. You have an entire 2 pi orientation, so it might be partially, southward or partially northward and everything in between. So you're missing this part of the problem. And then the other question, a practical one, in that brain diagram, what are the axes?
No one knows.
No, what do you mean no one knows?
If someone knows, I'm very curious myself. I don't. I tried. They don't have a physical representation. So it's a 7-dimensional space embedded in a 2-dimensional graph.
What's the bending way? There has to be an embedding way in order to preserve these, to present these 7 dimensions into a 2-dimensional. There have to be some coordinate transforms.
There's a lot. I can give you the paper. I have read it, but I would have to say I don't know.
Okay, thank you.
Do we have more questions from the auditorium? Please.
So in order to define geoeffectiveness, you basically have a hard threshold, right?
No, it's quite the threshold was the class of the DST disturbance, which we set it to -30 nanotesla, which is a weak storm. So there's no model like threshold.
Have you also discovered events that are right at this threshold that you set for this one, for the DST?
I wouldn't know the distribution on top of my head.
Okay.
No,
I was just wondering if you get false detections when you get close to the threshold, for example. In that case,
I'll have
this is
to
an issue.
No, we did not run this experiment. The problem, we did run the experiment on just moderate storms, which is -50, but it's not working as well because you miss a lot of storms. So there's a lot of in those 200 events, if you're cutting out 10, 20, 30% of it, this stops working. So we're at the edge of it barely working. That's the problem. So we tried, we started with severe. No, we went to moderate. No, with weak, we started to get good, reasonable metrics.
I see. Thank you.
But I can look it up and tell you the exact number. I think I have that distribution somewhere.
Do you think projection effects in the solar parameters that you have taken, speed, angular width, do they affect your output? Because angular width of CMEs cannot be greater than 180 degrees. And if you're considering a CME with a width of, let's say, 270, it might not be the case. It might be 150 and not 270.
The only answer I would have for this is that not including the angular width, removing one set of parameters made it not work.
Okay.
So I think it's important, but we had to use number angular widths for the model to work. So there's no halo. It's 360, and so on with a separation from 0 because of the trigonometry. But yet,
So
yeah, I think it's important. I wouldn't know what to answer you on the uncertainty that the CDO procedure does. It's pretty automatically, so at least you would think that that uncertainty would translate globally. But no, we did not try to evaluate this.
right, and the 0.7% of your geoeffective CMEs, are they all halo CMEs?
No.
No, so they are of width greater than 60 degrees.
I would think that's a yes.
Right.
I don't know if there's any of them that's smaller than 60. I think not.
Okay, thank you.
We had a question.
So you mentioned when you're thresholding, you take some, like, when the algorithm spits out some number, that number, if it's larger than some threshold, you take that to be geoeffective.
Yeah.
Why is it desirable to have it be like 0 or 1 rather than using the output as more of like a probabilistic estimate? That was kind of mangled. I can rephrase if you want.
That's because you would then need to define some manual classes. You would then complicate the issue into not really geoeffective, maybe geoeffective, potentially geoeffective, and really geoeffective. And for 200 events, that's not a good approach.
Something like the Breer, like a Breer score for for terrestrial weather, right? Where the classification can still be binary 0 or 1, but you get an improved score if you get closer to the right answer, right? So if you predict that there's going to be a storm tomorrow with 70% chance, and it storms, you get 0.7, whereas if it doesn't, you get 0.3. And that way you can kind of make the estimate more probabilistic. Is that desirable in this case or no?
I would say that's very desirable. We did not touch upon this.
Oh, okay.
So I am very interested to discuss it more.
Happy to do so.
Any more questions? Rosie has the question, please.
Okay. About the identification of geoeffective CMEs, you use the Richardson and Kane list
Yes.
to say that, okay, we have, if you're interested in another catalog, it's a smaller one starting from M-class flares associating CMEs up to there. But if you want really CME to flare connection done by observer, I would like to sell our catalog. I don't know if 2000 plus is sufficient for machine
What
learning
year?
tested. 2 solar cycles.
That's big.
Yes, it is.
That's
Okay.
quite big.
It's
I'm
published. You
interested.
can have it if you're interested in testing this on 2000 event list.
So this is
Flare
flare
to
to CME.
CME.
This
Yes.
this is what I said we're missing.
Yeah,
That-
it's the largest. Well, M and X classes. You can add the X classes, which I would say it's the majority of your geomagnetic storm anyway. So if you want to test, I gladly sell our stuff here.
That
Okay.
would be fantastic.
Okay. That's the comment.
So now we don't have online questions, looks like. Any more questions from the auditorium? So, okay. Thank you, Alin.
Thank you. Again, this is Andrea, not me.